To move that last electron, and we'll call this one the last electron because as they came down here they pushed the other electrons out all over the plate. That requires carrying it through a voltage difference of delta V. The capacitor is fully charged, so you have plus V, 0 V, so the delta V is just delta V. The work required to do that is Q delta V. We've used that a few times earlier. The charge on an electron is negative E, and the difference in potential for the last electron is V. The work to move that electron is equal to negative E times negative V, or just EV. The work to move that first electron was 0 because both plates were at the same potential, so to move an electron along an equipotential surface takes no energy, no work. The work to move the last electron was EV. Now the average work to move all the electrons is going to be EV over 2. And we can use that average value because the voltage decreases linearly from the top to the bottom plate. So we can just take an average of the two works and find out that our average work to move the electrons is EV over 2. If I'm now moving a total charge, not just an electron, total charge Q from one plate to the other is given by work equals QV over 2. That energy is now stored in this electric field that was created by the separation of charges. So that is, as mentioned earlier again, that's one of the functions of a capacitor. It stores energy so you can use it at a later time. The energy stored in a capacitor is given by U sub C equals QV over 2. U stands for potential energy because this is energy that we're storing and can use it later. Q is the charge on one plate. Don't make the mistake of trying to add the charges and get Q plus Q and 2Q or anything like that. We're just interested in the charge on one plate. V is the voltage difference between the plates that is initially supplied by a battery. UC is the stored potential energy. Note, the top plate is charged to plus Q, and the bottom plate is charged to minus Q. So the sum of the charges after being charged up is 0, just like it was in the beginning when it was neutral, when it had a 0 charge, due to conservation of charge. We can now use the definition for capacitance, C equals Q over V, which is over here again, and our equation for electric potential energy. And we're going to find two more expressions for potential energy, which will enable us to solve for the energy depending on whether we're giving the charge, the capacitor, the voltage, whatever. So let's take the capacitance equation, C equals Q over V. We'll solve that for V. V is equal to Q over C. We will also solve it for Q. So I have the three different expressions for the definition of capacitance. I will then take each one of these guys and substitute it in to the equation for potential energy. We have QV over 2 here, QV over 2 here. For this first column, we'll substitute in for V. For the second column, we will substitute in for Q. So I'll take you through the first one, and then you can work this on your own. UC equals QV over 2. I have Q over 2 times V. V is Q over C, and I get potential energy is Q squared over 2C. And if I go down this column, I get potential energy is 1/2 CV squared.